Good morning. My name is Kazuko Gray. It's my great pleasure to introduce today's plenary lectures by Dr. Minhan Dai from Sherman University. Let me briefly introduce about him. He graduated from Earth Science University Pierre Marie Curie, Paris, France, in 1995. Then he moved to Woods Hole Oceanographic Institution, and he spent several years over there. And since 1998, he has been in Sherman University, first as an associate professor, and now as a dean of College of Oceanography and Environmental Science, also director, State Key Laboratory of Marine Environmental Science, and also adjunct scientist of Woods Hole Oceanographic Institution since 2002. His research interest is carbon biogeochemistry in marginal and estuarine systems, and geochemistry of radioactive elements in surface and groundwater. Also, geochemistry of trace metals in coastal and estuarine environments. He has published more than 80 papers in leading international journals, and today his seminar is Coastal Ocean Carbon Cycling, Current Understanding and Challenges. Please start.
Thank you, Kazu, and it's truly an honor to be here to give this talk, and I'd like to thank the organizing committee for the invitation. Today I'm trying to share with you some of the recent understanding of the coastal ocean carbon cycling, and as you can see, I'm highlighting here two coastal systems, river dominant margin and ocean dominant margin. For the river dominant system, it's very clear because we are standing at the coastal ocean. We are seeing input from the river. And today I'm trying to also highlight the ocean dominant. We try to look at another boundary between coastal ocean and the open ocean. This is a little bit the overview of this on my talk. Coastal ocean links the atmosphere, land, and the open ocean. This is a missing but very important component in the global climate change models. And the coastal ocean CO2 flux has been converged, which should not be away from a moderate sink at a very global scale. However, mechanistic understanding remains very limited. And I'm going to show you, at least in some coastal systems, circulation and interaction with the open ocean actually lowers the coastal ocean carbon flux. So I'm trying to walk you through why coastal ocean and why coastal carbon, and give you an update of the coastal ocean carbon budget, primarily CO2 flux at the LC interface. And my main talk will be focusing why is a coastal ocean a source or sink to atmospheric CO2. And I'm trying to show you the contrast between river dominant margin and the ocean dominant margins. And then I'm trying to show you actually this is a continuum or spectrum of carbon transport from river to the ocean. In the big context of the global ocean carbon or climate change or ecosystem change, coastal ocean is a very unique system in terms of physical and biogeochemical coupling, because it links the land and ocean. Again, it's a very important component in the climate system. And coastal ocean, of course, is characterized by very complex circulation, abundant river and groundwater import, dynamic sediment boundary layer, and a very high productivity. So you'll see everywhere in the coastal ocean very large gradient, both in terms of chemistry and biologically. And here you see the surface area of the coastal ocean, of the global coastal ocean, about 8%, but productivity is about close to 30%, And then the carbon barrier, organic carbon barrier, is even bigger, close to 80%. And I didn't mention actually the gasification represents 50% in the coastal ocean. I put a very simplified way to look at the coastal ocean carbon. We are very familiar. We're talking about the air-sea interaction, and you have the biological pump that draw down the PCO2. Again, you have the two boundary layer. One is at the land-ocean interface, and also at the exchange with the open ocean. And the primary, the air-sea exchange is actually determined by the buffer capacity as well as atmospheric CO2 level, because of the rise in atmospheric CO2 will drive the CO2 into the ocean anyway. And we know solubility pump is overall another process modulate or uptake the CO2, but I would say it's actually in the coastal ocean it's not that important, because the solubility pump stands for the enhanced dissolution of CO2 gas into the cold water and the transport with the thermohaline or formation of deep water get into the deep water. But temperature in the coastal ocean also has a very important role. Biological pump or carbon barrier, of course, is very important as well in the coastal ocean. Again, this talk will try to focus or emphasize the terrestrial input and the exchange with the open ocean, how these affect the coastal ocean carbon. So I start with the big picture or big characteristics of the coastal carbon cycle. The first of all, it's very dynamic. Here you see this is an example of the Pearl River estuary, a long distance from the Pearl River estuary mouth. You see within 300 kilometers, you see huge PCO2 variability in terms of the space, and also you see different seasons, very large variability in this kind of a system. Another example showing here, I have a buoy system in the East China Sea of the Yangtze Shanghai. Actually, it's about time series 2 years. Again, you see huge variability in terms of PCO2. There's a partial pressure of carbon dioxide from less than under 200 to higher than 900 microatmosphere. Just to recall, the atmospheric CO2 level is around 400 or 380, something like that. So again, you see large, very dynamic system of CO2 change. And if you look at the global scale, you see again these dots in the different coastal oceans. And the color, the warm color means the degassing from the ocean, and the cold color is a strong sink or uptake from the atmospheric CO2. Again, you see large variability in the global coastal oceans. And the coastal ocean carbon is also changed. And this shows the pre-industrial coastal ocean is actually a net source, primarily because the organic loading or the heterotrophic loading and the gasification makes the pre-industrial coastal ocean as a source. At that time, actually, the nutrient or autotrophic loading was very low. Another point I'll make, the feature of the coastal ocean carbon is the increasing anthropogenic forcing. You see the worldwide eutrophication, hypoxia, ocean acidification actually all affects the coastal ocean carbon. Showing here is an example of how hypoxia will enhance the pH change in the current and the future scenario. This is, of course, will affecting the CO2, LC CO2 fluxes. So it's a very obvious when we dealing with the coastal ocean carbon cycle. Three primary questions are carbon flux and budget, because we want to know this budget in order to be included in this the global climate system model, and of course the control. The question obvious is why some of the marginal system source and some are sinks, and how are the coastal carbon are changed. I'm primarily focused on these two the first two aspects of the coast carbon cycling. So first of all, I try to show you the updated CO2 flux. This is the budget. And this was about 60 years, Wei Junkai and myself, and actually we tried to compile all the data available at that time. And this was and categorize all the global coastal ocean as 7 provinces. And then we come up with 0.22 petagram carbon. That means 10 to 15 gram carbon per year. And recall the global ocean, based on the Takahashi, it's about 1.4 without any correction to the atmosphere IRC interaction. So it's approximately about 20% of the global ocean uptake in terms of the CO2 fluxes. And if you look at aerial, it's about twice high in terms of sink as compared to the average global ocean. And more recently, Arthur and Borges came up with another number, around 3.3 petagram carbon per year for the global ocean to uptake atmospheric CO2. And again, you see different province has a different source and the sink. And this is the sink term. The red bar is the source term. So if we come up together, based on the Kai et al., Chen and Borges, and Borges again, actually, you came up with the approximately, again, it's 0.3 petagram per year as the global coastal ocean uptaking the atmospheric CO2. Another piece of the research is by K.K. Liu as synthesis work by the task team, the continental shelf, and they came up with a very similar number, 0.3 petagram carbon per year. So overall, it's quite a bulk part of the CO2 flux in the global ocean has quite a good consensus. So it's not very far away from the moderate sink, or twice or high, 2 or 3 times high as compared to the global ocean average CO2 sink. So the next question, very obvious, is why some of the coastal ocean are sources, while others are sinks to atmospheric CO2. And conventional wisdom, of course, the normal, we know the temperature, we know the heterotrophic loading, we know the export efficiency or net primary productivity will affect the coastal ocean carbon cycling. But if you look closely at all the distribution of the coastal ocean CO2 flux in terms of source and sinks, you actually do not have a very clear latitude trend. And we initially think the low latitude actually degas CO2 from the ocean to the atmosphere, but it's not really true. Actually, you see in high latitude, you see upwelling east boundary system. So this kind of the explanation cannot fully explain or resolve the question why some of those are source and some of those are things. So my new hypothesis is actually, in addition to these processes identical to open ocean, like temperature, biological pump, both land input and exchange with ocean interior are significant determinants of the CO2 flux in the coastal ocean. And there is at least 2 distinct settings if you look at the global ocean. One is the river-dominant margins, and another is ocean-dominant margin. So I'm trying to show you some of the examples why these systems are different. First of the river-dominant margin, you see everywhere actually the downstream of the large river system, like Mississippi, Yangtze, Amazon, Pearl, you name it. I'll show you some of the examples. This is the PCO2 in the Amazon plume. You see clearly, actually, in the spring and summer, when the discharge is large, you see drawdown of PCO2, for example, here, the cool color of the PCO2. And you see removal of dissolved inorganic carbon by this discharge-enhanced productivity. You see pretty much the same in the Changjiang plume in the East China Sea. Again, this is Shanghai. You see the cool color, that means low PCO2, and down to actually 90 microatmosphere. Again, this salinity, you see clearly the low salinity plume traveled actually far, can reach 500 kilometers or even farther from the mouth. And you see a very significant drawdown of PCO2 here in this kind of plume system. And a college in Taiwan has a very nice summarize between the discharge plume area, surface area, and the chlorophyll, that means productivity, and the drawdown, the PCO2. Essentially, you have the large discharge, you have the large plume area, and then you have the high chlorophyll, and then you have significant drawdown of PCO2 because of the photosynthesis uptake of CO2. If you look at the Mississippi, it's very similar. I'm showing here at the different salinity range, the net community productivity, that means the net uptake of CO2 if you want. And except that the immediate, the low salinity range, you have high net community productivity. That means you see the drawdown of CO2 in this kind of the range of area. Here is from Wei Junkai's data, actually clearly see the PCO2 in cool color because impacted by the plume. So if you move to the Pearl River, it's another large system close to the Guangdong area. This is Hong Kong. Again, you see the large plume. This is the case of 2008. And then you see drawdown in the plume area, a very low PCO2 level. Okay? So actually, it's pretty much the concept showing this diagram actually. In the lower estuary or in the plume region, you see very typically very enhanced primary productivity and uptake of the CO2 into the system. So the question of what contributes CO2 flux in the RealMar, or real marginal, river dominant marginal seas, essentially you have the heterotrophic loading, you have the autotrophic loading, as well as DIC. Those combination of those actually determines how the system will respond in the shelf system. Essentially, in the large dominated by the or the autotrophic, that nutrients loading, that will enhance the productivity and uptake in the plume region. Of course, this is a very large seasonal and spatial variability. And so this kind of system has a very strong seasonality along with the river discharge. And because of the heterotrophic and autotrophic, will lead to the community metabolisms. The net effect will be determined by the community metabolisms. Of course, sometimes we have the calcification, but it's rarely observed in the river plume system. Of course, it's also determined by a rising of air CO2 because of the fossil fuel emission. So let's look at another system, the ocean dominant margin system. I will primarily focus the South China Sea as an example, and actually very likely like the system like Caribbean Sea or Japan Sea is very similar. South China Sea is the world's largest marginal sea of Pacific, and the basin area is quite orogenic, and it has large river input from Pearl and the Mekong rivers. This shows the South China Sea exchange with the Western Pacific. Essentially, you have the very deep seal from the Luzon Strait has a depth of 2,000 meters. So there is a kind of a sandwich inflow, outflow flow exchange pattern with the Pacific, inflow in the surface upper layer, outflow in the intermediate, and overflow from the Pacific deep water inject into the South China Sea, and making actually the South China Sea the very strong upward moving. If you want, you can regard it as an upwelling system. And the result, the water residence time is very short, shorter than 50 years. And this I'm showing here is the integrate in 11 years. The CO2 essentially is warm color. That means essentially the basin area of the South China Sea is degassing into the atmosphere. And if you look at the zonal distribution, essentially I'm looking at this region. It's essentially a source. and that means degassing. So the question is why South China's release CO2? Essentially, the hypothesis is that because the overflow of Pacific deep water actually has the very high DIC relative to nutrients, DIN or nitrogen, inorganic nitrogen or phosphate, and with the upward motion of mixing up, and when you get to the surface of euphotic zone, actually the phytoplankton consumption is actually at ratio of the 100 in terms of DIC and the phosphate. So as a result, the photosynthesis of biological activity cannot overcome the excess DIC or dissolved inorganic carbon surprise from the depths. So I'm trying to use the field data to validate this kind of hypothesis. This is I'm trying to compare to the summer and the winter. And the first thing we try to build up is that the vertical mixing dominate this kind of material transport below the mixed layer at the South China Sea Basin. So we are using very simple 1D advection diffusivity model. This is the line is the model, and this observation. So this exercise actually tells you below the mixed layer, the material is quite well 1D dominate. Actually comes from the depths. And then we try to build up what contributes the mixing in the mixed layer. And we assume that actually it's a very simply in the basin area, less influenced by river input. We can build up very simple two-end member between rainwater and the water immediately below the mixed layer. And we use the total alkalinity and the calcium carbonate as the conservative tracer. Actually, it's quite well. So the mixed layer actually is a two-end member mixing. And then we use to the DIC or dissolved inorganic phosphate and come to compare these two mixing lines with the measurement. The delta, the difference between the measurement and the conservative mixing is the removal, okay? Removal, in terms of DIC, there is two components with the gas exchange and the biological uptake. And the phosphate is solely by the biological activity. So using a very simple residue ratio, if the delta DIC minus DIC component by the biological component, if DIC is over zero, that means there is actual DIC removal in addition to the biological activity. That must be the gas exchange because we don't see any calcification here. So we use the summer data and calculate the dissolved inorganic carbon difference, and using this difference, we can, using the Revel factor, actually we can turn into the PCO2 difference. This is the calculate or predicted delta PCO2, the difference between air and the seawater partial pressure, and you get the positive number of 44. Actually, the observation here is about 40 microatmosphere, so it's a perfect match. So we are looking at another case, is the winter case. Very similar, we are drawing a very large, but it's a little bit large uncertainty. And the field observation is about 10 to 0. So in the winter case, it's essentially that's equivalent of a very weak source of CO2 in the winter. So it came up with a very simple diagram, the conceptual of the LC in this ocean dominant margin. You have the exchange with the open ocean, depending on the depths of the DIC and the nutrient ratio, because if you have the access to the DIC, will be degassing when it moves up to the surface ocean. And at the same time, you have the biological activity here. So depending on the DIC and DIN in the source water, and also residence time, and how much time it will take from the deep ocean to the surface layer. Okay, actually, some of my speculation for the other possible ocean dominant margin would be very likely for the Caribbean Sea, because a very this is a largest margin sea of the Atlantic, and situating at a very similar latitude as the South China Sea. And there is also various deep passages larger than 1,000 meters. So this is a very similar system, I would speculate. And if you compare between the South China Sea and the Caribbean Sea, you have the lower DIC and DIN ratio in the Caribbean Sea. That means the excess DIC in the Caribbean Sea would be less. Actually, coincidentally, this system is a weak soil neutral in terms of CO2 flux in the Caribbean Sea. But I don't want to go too far from there. Japan Sea is actually a different system because the exchange with Pacific only with the depth less than 140. So it's lacking of the deep source of excess DIC in this kind of system. So if we want to put together the comparison between RILMA and the OSMA, if you want, it's determined, the RILMA determines river import of DIC and DIN TOC, and the combination and the comparison of the competition of this heterotrophic and autotrophic loading. And the OSMA actually is largely determined with the exchange with open ocean of the DIC and DON at different depths and the different residence times. But overall, if you want to take a mass balance approach, DIC versus the variation with time, you have the DIC mass balance with the net ecosystem classification and net ecosystem productivity plus the LC exchange flux. So you see actually the local effect typically are affected by net ecosystem classification and the net ecosystem productivity. But external source is primarily DIC. So I'm not sure how much time I'm left. So okay, that's fine. So the rest of I'm trying to give you some example. Actually, the river margin and the open ocean connection is a spectrum. It's connected. So trying to show you some of the river import and the groundwater import forcing into in terms of the carbon into the coastal ocean. First of all, it's well known about the river import. This is a recent compiled the global river influx in terms of DOC, dissolved organic carbon. It's turned up at the lower limit than the previous estimation, about 0.17 petagram per year. And I noticed that actually 60% of this dissolved organic carbon loading is concentrated at the lower latitude between 30 degrees north and 30 degrees south. Okay? And I'm trying to emphasize actually beyond the river import, we all know very well, we have the groundwater discharge. And this is the case of the northern South China Sea case in the summer wet season. I tried at 2 points actually. One is the flow rate. If you compare the river flow rate in terms of 1.8 cubic kilometers per day, and you have the flow rate of the submarine groundwater discharge about 0.3. It's about 17% of the river discharge. And also, if you look at the heterotrophic, the DOC import about 16% as compared to river. And very dramatic as a DIC because groundwater is characterized by its very high concentration of DIC. Secondly, because the ratio of the heterotrophic and the autotrophic ratio between river and the groundwater and the continental shelf on marginal sea are different. So that poses a very significant fractionation when this kind of carbon gets reacted in the coastal system. Very similarly, we have the East China Sea system. Again, the flow rate of the groundwater, submarine groundwater discharge is including both the freshwater groundwater and the recirculated groundwater. That's about 18, okay? And the DI is very similar level as the Pearl River. Again, you see difference between DOC and DIN ratio and the groundwater and the shelf system. Very quickly, South Atlantic bice, probably this is a very well-studied system in terms of groundwater. And again, is you have the dominant, actually overwhelmed groundwater, submarine groundwater discharge into the system as compared to the surface river. If you go to southwest Florida, actually groundwater flow is 10 times higher than the river, surface river. So again, this kind of system is very important by looking at both the river, surface river, and the groundwater discharge. Another actually not very paid attention is this is the example caused by Typhoon Morocco. It's a direct injection of carbon freshwater by hypopycnal flow direct into the deep ocean at the depths of 2,000, 3,000. So this is actually a forgotten carbon input into this kind of very dramatic input. And but we don't know much about the carbon. And in this case, about the Typhoon Morocco actually bring about 2,000 millimeters of the precipitation, and 10% is injected into the deep ocean at the 2,000, 3,000 meters. Carbon export. How much time am I there? Summary, okay. Carbon export is very complex, and in addition to the influence of the open ocean to I just show you ocean dominant, carbon export another thing. It's proposed actually back 10 years or so ago by Sunuga as transport from shelf to basin, so-called continental shelf pumping. Essentially, the cooling of the nearshore in winter forms high-density water that will mix up into the open ocean. Expanded continental shelf is very nicely summarized by K.K. Liu. It's a suite of physical process will be affecting the transport from shelf to the basin. Okay, I skipped this away. To summarize this river-ocean margin connection, river-ocean has about 0.17, and TOC probably is less than 0.3 petagram carbon per year. But we see nutrient loading has been increasing. Submarine groundwater discharge are yet to be better constrained. There does exist physical loss potential for carbon transport for the cross-shelf or cross-slope transport, but the global flux is very difficult to constrain. Carbon dynamic transport are very complex in the continuum of river shelf margin of open ocean, and much remains unknown. So I summarize here is the coastal ocean carbon is extremely dynamic in both flux and control and the time and the space. And the challenge remain at regional scale and counting CO2 flux both temporary and spatially. Mechanics understand is to be improved to better modeling the coastal carbon cycle to improve our predictivity capacity and the future climate change forcing. And land input in particular, the submarine groundwater should be better examined. Ocean margin interaction actually are three-dimensional. Okay? Ocean margin not only export but also receive. This is very much determined by the DIC and DIN ratio, and its biochemical implication should be better looked. Mechanics metabolism is still the key to quantify LC CO2 flux, but physical and biochemical coupling is essential. And I see actually there is a real need for an interdisciplinary global linkage between terrestrial, coastal, and ocean community. Thank you very much.
Thank you very much. It was very interesting and very concept and ideas for me, even for me. Thank you very much. Unfortunately, the time is quite limited, so I have to move on to the next session. So please see him at any time during the conference and discuss with him together. So thanks again for his nice talk. Thank you.